It's hot.
Is this a chemical reaction or a physical reaction that made it hot?
I think you're using a Jedi mind trick. I really don't know what that is.
I'm radiating heat into your coffee.
Silly.
Physical change. All right. We're going to hit up heats of reactions and chemical changes.
Yeah, so delta H now is what we're going to call that.
And we use a reference table I. The only reason this is here in this unit is because this unit talks about changes in heat. These are chemical reactions changing heat, and this is the only time in this unit you're going to see it. It's strictly learning how to use table I.
Pretty much. So real quick, endothermic means that heat is entering the system. And what you need to know now is I will have a positive delta H value. So that's key.
The heat of the system has increased because heat entered it. That's why positive sign would show up in front of the delta H. And H stands for what?
Entropy.
Heat. Right. And that's measured in joules.
Yeah.
So exothermic
would be the opposite. Can we make a note real quick here?
Yeah.
What side of the equation is this going to show up on? Because I know I didn't put this anywhere else in the notes.
If we have a chemical equation,
yes,
and heat enters it,
yes, it's got to be a
reactant.
There you go. So if you see the word heat on the reactant side or a plus like 340 kilojoules, you can get a number. If it's on the reactant side, it's endothermic.
Right. So
you might want to put a little side note in there.
Heat and equations can show up as reactants or products. That's what Mr. Milks
We're going to ask you to treat them that way too.
Yeah. Now exothermic
is the opposite.
Heat exits the system.
Yes.
So if the system has less heat than when it had started,
it must have negative heat.
It's like I got money, right? If I got money,
it's entering your pocket. You got
I got plus monies.
And if you're losing money, now you got negative
minus monies, especially. And we're at damn.
There you go.
Sweet. Almost out.
But here's the equation. It's always products minus reactants, no matter what we're dealing with. And even in this case, now we're dealing with heat. So now it's heat of products minus heat of reactants.
Right.
And when I'm dealing with an exothermic, that delta H just means there's more heat in the reactants. So hence heat exits the system. There's less heat in the products in order for me to get that negative value of mass.
If you wanted to think about it this, like we measured the change in mass of a system before and after and it didn't change, but heat doesn't have mass, so it can change. So if you had more heat before and less heat after,
then it must have left.
It left, so I'm at a heat deficit. I have a negative delta H.
Now it's going to be the opposite now for endothermic because heat is entering the system. So that positive delta H means there's more heat now tied up into the products. It entered in.
Right. It came from all around. Maybe it was a burner that I had to put heat in to make it happen.
Sure. Right. To get the water to boil to make some noodles.
Well, that's a physical change.
True.
We're talking chemical change.
Oh, yeah, you're right. Thanks. It's late. All right. Right off table I.
These are equations that are listed on table I. They're given a delta H value to you straight off the table.
You got one behind you. Grab that.
The part that you need to interpret from these notes is if that delta H means the reaction is exo or endo.
Right, so we're going to look it up real quick on table I. Show you what it looks like.
Table I, heats of reaction, 1013 kPa and 298. Standard temperature and pressure.
Ooh, yeah. So negative tells me right off the bat that it is
exothermic.
And if heat is exiting the system, I have less heat. And so this is what that sketch is going to look like.
Right.
I'm going to start off with more heat, and then I'm going to react, and I'm going to finish with less heat. So
we lost heat. For exothermic potential energy diagrams, you lose heat. We'll see that in another unit later.
In detail.
This was our first introduction of it, so I figured, keep it simple.
Yes.
Now, let's see a different chemical reaction. Because we're going to hit all the options, right? We had an exo, we'll probably have an endo.
Yep.
Notice what the delta H value here is.
Positive
66. So just a little bit of energy has been added and absorbed by the system.
So now we're endo. So now I'm going to start low.
Go with blue.
High.
Yeah. Okay. So he starts with less energy than he ends with. And so this is a sketch of what the reaction progress would look like with respect to energy.
Sure, the bottom flat would be the reactant side. The second flat would be the product side.
And the hump is the arrow, so to speak.
Where the reactions happen.
Yes. Now this next reaction, let's see, this is on the period. This is just another one off the table. We didn't do anything funky to them.
No.
Not playing tricks. So this one's negative 483.
Negative tells me right off the bat that it's exo.
Heat release.
I have less students. They have exited my room.
I have less money in my pocket. It exited my pocket.
Exo.
Bank account.
That sketch is going to be
just like that again. Mhm.
The first one that was X.
Now, what we can ask is, compared to reactions, which one releases more energy?
We could, and that would be the one with the bigger negative value.
Right, the larger number with a negative sign.
Right.
Or we could ask which reaction absorbed more energy, and that would be the one with the larger number with the positive sign.
And here's another one.
There we go.
Positive sign right off the bat tells me that it is
Endothermic.
endothermic.
Soaks up heat from the surroundings.
So the reactants have some energy, they react, and they have more as a product. Heat entered the system.
Typically, reactions that are endothermic produce products that might not be stable sometimes.
Well, because they have more energy.
They prefer to have less, and so they might react in
That's
reverse, which
That
is a whole
is
nother
nature.
unit too.
Right. So there's one piece that we didn't touch on in the actual notes. Now we're going to see if you're listening.
Yeah.
Because there's games we can play with these. So are you listening?
What?
Can you hear me now?
Can you hear me now?
Can you hear me now?
Lay it on me, Mr. Milks. What?
Ready? All right, here's the game we can play. If I double the reaction, you
Mhm.
find this particular reaction that's listed for you, but you have 4 moles of water reacts to form 4 moles of hydrogen gas and 2 moles of oxygen. I just doubled the reaction. What do you think I should do to that delta H?
Double it.
Double it. That simple.
Yeah. For sure. Like,
And if
you want to think about it like this, if you're talking about, let's show a exothermic one.
Okay.
Exothermics are easy to. There you go. This is the formation of water from hydrogen gas and oxygen. It's literally explosive and one of the fuels they use on the rocket ships.
yes,
Right. So it releases a ton of energy. Exothermic. Now, if you think of that as, imagine it as just one firecracker.
right. If I put in 2,
You're going to get double the energy, double the bang.
Yep.
So if you double the mole ratios, you double the amount of energy.
and that works just opposite. If I half the mole ratios, I will get
Half the energy.
half of it.
So that wasn't in the notes this unit.
No.
We're going to hit it up more in kinetics. But it is important to just kind of know, get your feet wet, kind of
Yeah,
understand.
and we
like,
did it in the practice that's coming in. Some of the practice problems we redid for you. It is in there. So I don't want you to have any curveballs. There's one other curveball we could throw you though.
What?
What if I did the reaction in reverse?
Well, if the forward reaction was exothermic,
Then the reverse reaction would be
reversed,
endothermic.
endothermic, I would flip the sign on the value and I'd flip the direction of the arrow, and there we
That's it.
go.
But the number will stay the same.
Right.
The magnitude of that heat will stay the same. It's just now is it entering the system or leaving the system?
And to take my rocket fuel analogy, okay, if you take a gallon of rocket fuel in this ratio and you react it, kaboom, you release a ton of energy, and you got water. Well, if you take that water and you force the energy back into it, it would separate it back out and
It would
produce
take
the
a ton
other
of energy.
the same exact amount. Actually,
It would take a ton.
it would take a ton, but it would be the same exact amount.
It
So
would be.
if this reaction you see on the board releases 483.6 kilojoules
to do
of
the opposite,
energy,
I'd have to put it in.
you'd have to put in 486,
Right.
or 43, pardon.
Yeah.
So that's kind of it. So you can double and half or reverse these types of reactions. It's just, don't get scared by all that notation.
Yeah.
That's what messes people up.
We taught you a lot about that notation, about the reactants, the products, gases, liquids, solids.
All of it.
Right? And now we're just throwing that little piece in now with the energy. Where does energy come into that reaction and how does that play?
We
A
should
little bit
make
of
them write
practice.
the whole table I over and put heat in on the side of that reaction arrow, depending on delta H's sign.
Doing too much. You're
Yeah.
good. 1 page of practice. You get the hang of this. It's a piece of cake. See you guys.
I'm gonna put on my glasses to see.
Okay, do that.
What am I clicking on here?
Mr. You fucker.
Well, I think